The topic of this screencast is pH, acids, bases, and buffers. You will find information on this topic in Chapter 15 of your textbook. This screencast was designed to help you achieve the following objectives. Define pH. Explain the importance of pH in living organisms. Describe how buffers resist changes in pH. List the 3 mechanisms the human body uses to regulate pH and compare them by speed and effectiveness. List the 3 buffer systems of the human body in order of effectiveness. The normal range of blood pH is from 7.35 to 7.45. Blood is considered to be in homeostasis with respect to pH when it is in that range. If blood pH goes above 7.45, one is said to have alkalosis, where the pH is above or more alkaline than the normal range. And if it falls below 7.35, the body is in a condition of acidosis, where it is below or more acidic than what's considered the normal range. Most hydrogen ions originate as byproducts of cellular metabolism. So in other words, the body normally produces excess hydrogen ions. So to maintain blood pH in the normal range, which is slightly alkaline, remember neutral is 7, so blood pH is slightly alkaline. So obviously the body has several homeostatic mechanisms to help maintain blood pH in the normal range. Before we go any further in our discussion, let's remind ourselves of what pH is. So pH is a measure of the concentration of hydrogen ions in solution. If we looked at a mathematical equation, it is the inverse log of the concentration of hydrogen ions, the inverse log. So remember that as the concentration of hydrogen ions increases, the pH actually decreases. Also remember that the pH scale is in a logarithmic scale. So for every 1 unit change in pH, there is a 10-fold change in hydrogen ion concentration. If you recall from our discussion on basic chemistry, the pH scale runs from 0 to 14, where 7 is considered neutral. That's where you have an equal concentration of hydrogen ions and hydroxide ions. As we decrease from 7, a solution becomes more and more acidic. So 0 is as acidic as a solution can possibly be. As we increase pH above 7, it becomes alkaline and becomes more and more alkaline as we move toward 14. Again, the pH scale is a logarithmic scale, so something that has a pH of 5 is 10 times as acidic as something with a pH of 6. Something that has a pH of 4 is 100 times more acidic than a pH of 6. So you have a 10-fold increase, then you have another 10-fold increase, so that's a 100-fold increase in acidity. Blood pH, as I mentioned, must be maintained within narrow limits. The optimal range is 7.35 to 7.45. The obvious question is why? Why is pH so important? The answer is proteins. Proteins lose their activity when pH is either too high or too low. Why is that? Do you remember the hydrogen bonds? These are bonds, intramolecular bonds. So these are bonds between molecules, or they can be between different parts of a molecule. They are important bonds, but they are weak bonds. And a change in pH can break these bonds. And if they break the bonds, they can change the shape of a protein. And a protein's ability to function is dependent on its shape, sort of like your key. Your ability of your key to open your car door or any lock, your house, apartment, is dependent on its shape. Change the shape of that key a little bit, it doesn't work as well. Change it more than a little bit, and it won't work at all. The same is true of proteins. Let's look at an example of how pH can change the shape of a protein. And we're going to focus on an enzyme. Remember that enzymes are proteins, and they catalyze or speed up and control the rates of chemical reactions inside the body. Here we have an enzyme and we have a substrate. And recall that that an enzyme binds a substrate at what's called the active site. Notice that an enzyme, in order for it to bind the active site, has to have a particular shape that matches the active site. Again, like a key to a keyhole. One of the main determinants of the shape of any protein are the hydrogen bonds between different amino acids of that protein. These arrows here are highlighting hydrogen bonds between different amino acids of this protein. Again, these hydrogen bonds are mainly responsible for the shape of this protein. Let's say that the pH of the solution that this protein is in, or let's say whether it be extracellular fluid or intracellular fluid, depending on when this enzyme is found. Let's say it changes. What's that going to do to those hydrogen bonds? What does a pH change do to that protein? Well, it denatures that protein. It breaks those hydrogen bonds. That affects the overall shape of the protein. Now, it doesn't have a shape that allows it to bind the active site of the substrate. And for the most part, this protein can no longer function normally. This enzyme is not able to bind the active site of its substrate and catalyze the chemical reactions. Okay? Now, there are numerous proteins in the body that have functions. Hemoglobin, for example, that transports oxygen. You have proteins that act as protein carriers. You have proteins that act as channels. You have proteins that are responsible for many of the life-sustaining properties or processes that occur in cells, on cells, and sometimes in the extracellular fluid. So the destruction of these proteins, or the denaturation, I should say, of these proteins can render them inert so that they no longer function. Therefore, this is why blood pH is so important, and it has to be maintained in that normal range. In fact, there is an absolute low pH and an absolute high pH at which death occurs. The nervous system is depressed, leading to coma and death if the pH falls to 7. And if blood pH rises to 7.8 or beyond, the nervous system becomes overly excited. This results in tetany, convulsions, and extreme nervousness. And as a result of that tetany, uncontrolled contractions of muscles, including the diaphragm, that leads to respiratory arrest. If the diaphragm contracts and won't relax, you lose the ability to exhale. And the result is loss of pulmonary ventilation, and therefore the lack of the ability to oxygenate the blood. Despite the fact that it is necessary that pH remains in a normal range, there are many sources of hydrogen ions as a result of just normal metabolism. For phosphoric acid, for example, is released or produced as a result of the breakdown of phosphorus-containing proteins. Lactic acid, as we discussed in the chapter on the muscular system, results from anaerobic fermentation. Ketone bodies in organic acids are produced as a result of lipid metabolism, and carbonic acid is produced as carbon dioxide enters the plasma. So there are many normal sources of hydrogen ions in the human body. Therefore, it should be of no great surprise that the human body has various mechanisms for regulating pH. And they are chemical buffers, the respiratory system, and the kidneys or the urinary system. And I have listed these mechanisms in increasing order of effectiveness or power. Chemical buffers act immediately in response to a change in pH, but they're relatively weak. The respiratory system can take a few minutes to respond, but it is more powerful than all the chemical buffers combined. And your most powerful regulator of blood pH are the kidneys or urinary system. They're slow, they can take a day or more to fully respond to a change in pH, but they are the most effective. In this screencast, we're going to focus on the chemical buffers as a mechanism for regulating pH, and we'll cover the respiratory system and the urinary system in the subsequent screencast. If you recall, acids are proton donors and bases are proton acceptors. Let's focus on that in the next few slides. You ever wonder what the difference was between a strong acid versus a weak acid, or a strong base versus a weak base? Well, it all has to do with how well they dissociate when placed in water. Let's take hydrochloric acid, for example. Hydrochloric acid is a strong acid. I think most people are aware of that. Well, why is it a strong acid? Well, if you place it in water, it 100% dissociates into hydrogen ions and chloride ions. Well, what does that mean? Well, you won't find any intact HCl in a solution of hydrochloric acid. Everything in there is hydrogen ions and chloride ions. And it's these hydrogen ions that do damage. They will literally break bonds and try to retrieve electrons from those bonds. And they don't really care if those bonds is clothing or metal or your skin. And that's how they damage other compounds and molecules. Let's contrast that with a weak base, such as carbonic acid. Carbonic acid, of course, is carbonated water. You bubble carbon dioxide through water and you get H2CO3. Like hydrochloric acid, it is an acid. When placed in water, it dissociates into hydrogen ions and bicarbonate ions. But what's different is it dissociates poorly. Most of the carbonic acid stays intact as H2CO3. So when you look in a solution of carbonic acid, soda pop, right? There are very few hydrogen ions roaming around destroying other molecules. That's why you can drink a solution of carbonic acid, and we do, right? Pepsi, Sprite, RC Cola, but you would not want to drink hydrochloric acid. A similar relationship exists between strong bases and weak bases. Sodium hydroxide is a strong base. If I'm not mistaken, it's the active ingredient or one of the active ingredients in oven cleaner. Why is it a strong base? Well, if you put sodium hydroxide in water, it dissociates completely into sodium ions and hydroxide ions, right? So it's got a pH well above 7. So if we look at a solution of sodium hydroxide, we don't really find any intact sodium hydroxide molecules. It's all sodium ions and hydroxide ions. And those hydroxide ions, like the hydrogen ions, are unstable and they will break other bonds and they'll cause damage to tissues and other molecules. Contrast sodium hydroxide with the weak base sodium bicarbonate. Sodium bicarbonate, when placed in water, dissociates poorly into sodium ions and bicarbonate ions. So if we looked at a solution of sodium bicarbonate, we'd find that most of it is intact sodium bicarbonate, and we'll have a few sodium ions and a few bicarbonate ions, right? But not many bicarbonate ions. And that is why you can brush your teeth with sodium bicarbonate. If you're not familiar with sodium bicarbonate, it is baking soda. You can place it in your hand, you can place it in your mouth. It's not going to do any kind of damage to your tissues. You would not want to do that with sodium hydroxide. I think you can understand why. So why is it important to understand weak acids, weak bases, strong acids, strong bases? Well, weak acids and bases make good buffers, and buffers are chemicals that resist changes in pH. How do they do that? Well, as hydrogen ion concentration increases, or in other words, the pH decreases, they will pluck hydrogen ions out of solution, therefore resisting drops in pH. When hydrogen ion concentration decreases, causing an increase in pH, they will release hydrogen ions into solution. So in that way, they resist changes in pH, and weak acids and bases make great buffers. Because organisms are very sensitive to pH, humans included, we contain various buffers that help resist changes in pH and therefore keep pH in the normal range. They take up excess hydrogen ions as pH decreases, and they release hydrogen ions when there is a deficiency of hydrogen ions, right? So in this little illustration that I put together, here we have, let's say this is the normal, these two hydrogen ions represent the normal pH, right? And this is the buffer. Let's say something happens when there is an excess of hydrogen ions, right? So now our pH has fallen below the normal range, right? How can a buffer help return pH to the normal range? Well, the buffer will come along and pluck some of those hydrogen ions out of solution, helping to maintain the original pH. What if on the flip side, there is a reduction in the pH, right? We had two hydrogen ions representing the normal range, right? Now we're at 1. How does the buffer respond? It'll release those hydrogen ions into solution. So buffers help maintain blood pH by taking up excess hydrogen ions, and when there's a deficiency in hydrogen ions, it releases them. And as I mentioned, weak acids and bases make great buffers. There are three buffer systems in the human body that you're responsible for being familiar with. They are the bicarbonate buffer system, the phosphate buffer system, and the protein buffer system. And when I say you should be familiar with them, I'm going to show you details about these three systems, but honestly, I really only want you to be able to recognize them, that is, know them by name, and also have an idea of their relative strength. And as I did earlier, I have placed them in order of strength. So your bicarbonate buffer system is your weakest, your phosphate intermediate, and your protein is the strongest. Now, in the following slides, I am going to show you the details of each of these buffer systems, but I want you to understand that I am not holding you to these details. So in other words, I'm not going to ask you a question specifically about these details, but I don't want to simply have you memorize these buffer systems and you haven't been shown any information about them. So in the next slides get into a little detail about these buffer systems, but it's only to give you some perspective on them and some insight into how they work. But again, I'm not going to require you to understand these details. The bicarbonate buffer system is a very important buffer system in the extracellular fluid. It consists of a mixture of the weak acid, carbonic acid, and the weak acid, or weak base rather, sodium bicarbonate. To illustrate how it works, if we were to add hydrochloric acid to the extracellular fluid, the sodium bicarbonate would interact with it, yielding a weak acid, carbonic acid, and a salt, sodium chloride. So in this way, we start with a strong acid. When it interacts with the weak base, the result is the production of a weak acid. So it's resisting a decrease in pH by the strong acid. Likewise, if we add a strong base, that strong base would react with carbonic acid, resulting in the production of a weak base, sodium bicarbonate, and water. So again, the addition of a strong base results in the production of a weak base. And so that buffer system is resisting an increase in pH that otherwise would occur with the addition of a strong base, in this case sodium hydroxide. The phosphate buffer system is an important buffering system in the urine and also in the intracellular fluid. It consists of a mixture of sodium dihydrogen phosphate and sodium hydrogen phosphate as the weak base. As we saw with the bicarbonate buffer system, the weak base interacts with the strong acid to yield a weak acid and salt, and the weak acid of this buffer system interacts with strong acids to yield a weak base and water, therefore minimizing changes in pH. I want to stress again that I am not going to hold you to understanding these details. I am simply providing them so that you have an understanding in general of how buffer systems work. The phosphate buffer system is more powerful than the bicarbonate buffer system, and the protein buffer system is more powerful than the phosphate buffer system. So the protein buffer system is more powerful, is the most powerful of all three buffer systems. The proteins of the body, whether they be in the intracellular fluid or in the plasma, act as buffers because they can donate hydrogen ions when pH is high, meaning when there's a deficiency of hydrogen ions, and they can pull hydrogen ions out of solution when there is excess hydrogen ions. And this is because they are amphoteric molecules. They can act as both acids and bases. So This R represents most of a protein, right? So what you're looking at here is this is one functional group on a protein, right? This R represents the rest of the protein. So this R could be 50 amino acids. It could be 100 amino acids, okay? Our focus is on this functional group here. This is called a carboxylic acid. It's what makes an amino acid an acid. Well, that carboxylic acid will donate a hydrogen ion when pH levels are high. So in other words, when there's a deficiency of hydrogen ions, that hydrogen ion will come off, right? And in this way, proteins resist increases in pH when pH levels are high, when there is a deficiency of hydrogen ions. On the flip side, their proteins also have other groups called amino groups, right? It's where we get the name amino acid, the NH2. When pH levels are low, meaning there's a excess of hydrogen ions, these amino groups will pull a hydrogen ion out of solution, forming NH3. That resists a drop in pH when pH levels are already relatively low. So proteins in both the intracellular fluid and in the plasma provide resistance to changes in pH and therefore provide a very powerful buffering system by taking hydrogen ions up as pH levels drop and releasing hydrogen ions as pH levels increase. Now let's review the learning objectives of the screencast. Define pH, explain the importance of pH in living organisms, describe how buffers resist changes in pH, list the 3 mechanisms the human body uses to regulate pH and compare them by speed and effectiveness, list the 3 buffer systems of the human body in order of effectiveness. The topic of your next and final screencast will be regulation of pH by the lungs and kidneys.